everybody, we're on to 7.7b exponential decay. We're going to model what decay exponentially looks like. It's very similar to exponential growth, but it may be the opposite. So exponential decay occurs when a quantity decreases by the same rate that r in a given time period. So just like growth, the value of the quantity can be calculated using our original exponential formula, but since it's decay, our b has to be smaller than 1. All right, so if inside this parentheses, sorry, I had a brain fart there, this number is less than 1, it will be decay. For growth, it was bigger than 1. Decay will be smaller than 1. It cannot be 1, as we learned a couple lessons ago, because that would just make it linear. So again, this is just like our last for growth, but now I'm just changing it slightly to decay. Everything is the same in the formula. Y is the same. Did you notice this says yart? Not really important, but just that always jumps out to me. Anyway, Y is the final amount, A is the original amount, R is the rate as a, it's all over here, as a decimal. I'm not sure why it was all the way over there. And let me highlight yard again. And T is the time. All right, but the major difference here, please be cautious. We're going to do 1 minus r. So if I do 1 minus r, I'm subtracting away that rate. 1 minus anything will take me less than 1. My rate can't be negative, so it's not going to be like minus a negative. To increase it, it will definitely be less than 1 for being decay. All right, do a couple examples after I talk about this slide. The important difference is kind of what I just said. For growth, it's going to be greater than 1 because r is added. For decay, it's going to be less than 1 because r is subtracted from 1. Okay? Decay, you're subtracting away from r, it's getting smaller. Growth, you're adding, it's getting larger. Now let's get to some examples, okay? A population of a town is decreasing at a rate of 3% per year. In 2000, there were 1,700 people. Write an exponential decay function to model this situation. Let's do that first, okay? Again, it's nice and color-coded for you this time. 1,700 is my initial amount. That's A. I'm just going to plug it in there. My rate is 3%, so I need to convert that to a decimal, and I get Y 1,700 times 1 minus 0.03. Now, what some students do like to do is they like to, when I enter in the calculator, they'll just actually subtract that and just put that in the parentheses. You know, that's okay. But this, what I have right here in that gray color, that's my exponential decay function. And now I want to find the population in 2012. So if I want to find it in 2012, I got to do some math because the t is not going to be 2012. All right, that would mean 2012 years later. The initial amount was 2000. It jumped to 2012. You got to find the t. The t is just going to be 12 here. Plug that all in, and we get about 1,180. I know you get about 1,179.5 in a calculator. Try it out, but you can't do that. That's gross. That's nasty. You can't have parts of people. If we're dealing with people or anything in that we need a whole. Okay, we want a whole person. So we'll round up to 1,180 people in the town in 2012. Now let's talk about fish. Fish population in a local stream is decreasing 9%. Population originally was 48,000. Write a function to model this. So what do you think the model will be? Hopefully you came up with 48,000 times 1 minus 9%, which becomes 0.09 to the t power. Now find that after 7 years, the only difference is I'm just going to change that to a 7. I'm going to enter it in a calculator. And again, I'm going to get 24,805 fish because we have to round that up. Okay, can't have part of it. Well, I've seen parts of fish while fishing. Bigger fish ate it, left part of it, but we got to make it a whole number, okay? Now, this is the last little piece. There's an application of exponential decay is called half-life. I'm not really going into that much detail. It's not covered that much. If you do one of the aspire to do IXLs, it's in there, so I'll briefly explain it. It's the amount of time it takes for an original amount to decrease to half of its initial value. Substances like caffeine. Caffeine has a half life of about 8 hours, which means it takes 8 hours for half of the caffeine to leave your system. In another 8 hours, half of that will be gone. So it takes a while for something completely to get out of your system. The formula for it is A equals P. I don't know, I guess I'll uncolor code that because now you can't see down there. A equals P times 0.5, because it's half-life, to the T power. And the T represents the number of half-lives in a given time period. All right. Like I said, I'm not going into much detail because it's not anything I'm going to make you do. But if you want to go into more detail, you can definitely try it out. Your work is going to be 2 Khan Academy lessons and a mastery check. And like I said, there is an Aspire to do XIXL if you're interested in giving it a shot. It's definitely good practice.